that was circulated. He got his PhD at Iowa State in theoretical physics and is now a postdoc in the Department of Mathematics. And we're delighted that he, who is also the prime organizer of this seminar series, has agreed to give us a talk today on his subject. Looks like, thank you for sharing the title, saves me the trouble of trying to look back to the emails. Phase-encoded linear algebra with the Quantum Fourier Transform. Bo, without further ado, please proceed.
Sure, there we go. All right, hello everyone. I'm here to, as James kindly introduced, talk to you about phase-encoded linear algebra with the Quantum Fourier Transform. Specifically, this is more, our goal ultimately is to try to do linear algebra, and this is trying to, on a quantum computer specifically, and this is the path we're proposing we take to get there. As far as the contents of this talk, I'll start with a brief refresher and continue on to explain the Quantum Fourier Transform and what the Fourier basis is, along with, then we'll get into Quantum Add, Quantum Multiply, and how we'll use these for constructing and operating on quantum matrices. So as far as why quantum computing, largely the first big thing that everyone kind of gets into introduced to quantum computing and is excited about quantum computing is that quantum algorithms solve certain problems much faster than any known classical algorithms. Main examples include like Shor's algorithm, Grover's algorithm, like such as and quantum walks. And this is all sort of at a more fundamental level because these quantum effects allow for bit operations that are impossible to do on a classical computer, which we'll sort of get introduced to shortly. So the big question that we started here with in this the project I've been involved in is trying to just approach the question of what does linear algebra look like on a quantum computer, which with follow-up questions like how do you actually encode and operate on the information, and how do the properties of that information change compared to their classical analog? And the goals of the project are to develop a basic platform for starting to perform linear algebra, in essence, the basic building blocks, and to explore the properties of these quantum data structures and consider how to classify them compared to their classical analogs. And in general, just seek insight on identifying potential use cases so that we can start developing future algorithms. So when I talk about quantum data structures, and in this context, quantum matrices, I don't actually know what the appropriate term is, or if there is yet an appropriate technical term. But what I'm trying to refer to is a matrix with, in our case, integer elements that may each be in a superposition state. That is, like each element could be, say, the first element could be both 1 and 4. By being in a superposition of both, as represented on qubits, which I'll explain shortly. So the thing about quantum matrices, they possess analogous properties to pure matrices. And to be clear, we're going to only be talking about numerical matrices here, or at least the quantum equivalent. We're not going to be we're not really quite even going to try to dive into actually talking about any sort of representations with variables. We're going to just stick with the pure stuff, and that'll be plenty, because even though they have these analogous properties, they're distinct from pure matrices, and in general remain rather poorly understood. Like to give you an example, if for a classical matrix you have properties like invertibility, and certainly hermiticity is a big one in my field for nuclear structure. But for a matrix that for these quantum matrices, they're a data structure or a mathematical object that can be both invertible and non-invertible at the same time. because they have this superposition of their elements. So for instance, does that mean invertibility isn't useful to talk about? Well, no, of course not. It's still useful to talk about invertibility with a quantum matrix, but we're clearly not going to be able to talk about it in quite the same way. At the same time, there may be additional properties that don't have any classical analog. And to be honest, the more I've only just recently been getting to where I can actually start looking at the matrix side of this stuff. And the more I do it, the more I'm starting to realize I really don't have any clear idea how to properly talk about these structures as far as their properties. And it's not as though such a matrix has not been considered before. You can of course create such a matrix, and it has been done on a classical computer. The big difference is that these kinds of data structures, quantum matrices, and other various other data structures that will be like them, are data structures that will be native to these quantum computers that we'll soon have access to. And so if we're ever going to start using quantum computers, not just in this paradigm of computational basis, which again I'll be getting to, but we're going to need to start figuring out how to talk about these structures that will be native to quantum computers, because, and as I said, you can do them on classical computers, but the scaling is terrible. That's why we've never really needed to learn how to talk about such a matrix, because it's never been feasible. But this is something that quantum computers will be particularly good at, so we need to know how to use them. So that's my spiel. That's my elevator pitch. Why this is important. And now we're going to go through how we're going to get there. So now we're going to start just with the idea of qubits. This is just all introductory to make sure everyone's up to speed. So classical bits, you have states that are exact and deterministic, whereas with a quantum bit, the bit state can be in a superposition that collapses when we measure it.
Bo, could I just interrupt for a second? I found what you just said so fascinating. I have to ask a question.
Sure.
So if I imagine that I'm going to be able to solve problems which are coherent superpositions of matrices, and I think that's what you've said in the previous slide, that's the kind of problem that would be discussed here. In my language anyway, it would be some coherent superposition of matrices. Is that fair to characterize it that way?
If not precisely within like a transform, one can have quibbles on whether if this is a superposition of matrices or a matrix whose elements are in superpositions. But I'm pretty sure you can expand one to the other.
Okay.
So there is some transformation in between, but it should be functionally equivalent as far as in this context, at least as far as I'm aware.
Okay, insofar as this is related to a coherent superposition of matrices, I imagine an application in physics, which is wave scattering problems, where we have a wave packet of initial states, which is a superposition of, in effect, it's a superposition of Hamiltonian problems, a coherent superposition of Hamiltonian problems, because a wave packet says, I don't know precisely my initial state. I have to take a superposition of initial states, and my Hamiltonian will depend on which initial state I take. So I just wanted to see if maybe that's a realm of thinking that may be related to what you're presenting.
I'd honestly have to look into it. I know what, if I'm not mistaken, I know what you're talking about. In fact, I think we've talked about it a little bit before here and there. We don't, our group doesn't do as much of well, and that's not entirely even fair. I haven't done as much of the scattering stuff, but we definitely have been involved with it. But I'm not sure I can give an answer without looking more deeply into it.
Okay,
So
let's postpone it for further discussion later.
yes,
Thank you. Thank you.
it is an interesting suggestion. Okay. So qubit states may not be exact until we measure them, and their collapse is non-deterministic. That is, when we measure them, we irreversibly destroy the probability distribution, and we can't go back. It's not a reversible process. It's important to understand that when we're talking about this quantum superposition, this is not just a predictive tool we use in physics, but this reflects a fundamental property of nature at the quantum scale. And that's very important because it's largely why this is any different from just trying to talk about probabilistic computing or just like probabilistic gates, which is a field people consider gates that have a chance to be applied or not applied, but they're always either applied or not applied, never both, which is the distinction for a quantum gate. So we can apply unitary transformations to states without measuring them. This is very important because it's why we can functionally maintain this quality of superposition without and still actually have any sort of interaction with these qubits in superposition. But we can only extract information on the state through measurement. There's no way to try to use a unitary transform to gain any information from the system. So it's both a increase in your degrees of freedom, but also very constrained on as far as the information. It's very odd and takes a little bit to get your head around it. The state, what we'll be using as far as talking about in as far as the expression of states, these states of qubits, is Bra and Ket notation, which refers to where such a Bra or Ket refers to a physical configuration for one or more qubits, and may be expressed as a linear combination of an orthonormal basis in Hilbert space, such as this one, where this 0 here would represent some qubit string, as this one would represent some other qubit string, and these coefficients can be in the complex any complex number, and thus the linear sum forms this this state, this qubit state. A key characteristic of qubits is that multiple qubits can be in an entangled state that you can't describe independently. This here is an example where I'm now switching to where I'm going to use actually specify what the qubit binary states are in this expression, this ket, where if I have these two qubits in this state that is a sum of both this 0, 0 and 1, 1, there's no way mathematically I can decouple these. As soon as I know the state of one of them, if I go and try to just measure one of them, I will, because they're entangled, I will necessarily collapse what the other one is state the other one is in. For instance, if I measure a 0 on Q1, then it must be in state Q. Q2 must also be in state 0. Okay. So those are qubits, and this is the Bloch sphere, which is used to try to better comprehend where qubits live as far as the states. The vertical Z basis is the computational basis, and this is what we use in classical computing, where we have zeros and ones. But a qubit has the additional freedom of being able to rotate in this complex plane, and thus we have these additional states, which where it's the combination of 0 and 1, and then 0 and 1 over here on this y-axis, where it's now it possesses a complex magnitude. And sometimes you use these different symbols to represent these. It's just that's what IBM does. Different people do it different ways. I'll be using this a little bit, but it shouldn't show up too much. Okay, so now that we know what a qubit is, we can talk about the quantum logic gate paradigm, which must correspond to unitary operators strictly, which is also to say that they must be reversible. We are doing solely reversible computing when we do quantum computing. There's an infinite number of logic gates, but we only need a finite number to form a universal gate set in which we can construct all other gates from it. Now, that said, that doesn't mean that all universal gate sets are equal, or that all programs will run the same if your machine runs a different universal gate set. More on that later. Some standard 1-qubit gates are such as like the identity, the flip operator, and similar the Y and Z, which are actually in essence just flip operators in the other dimensions. And these are actually for physicists and mathematicians, the polymatrices. And this gate, the Hadamard gate, is a very important one because it functions as a Fourier transform and goes from the computational Z basis to the what will be the Fourier basis, and is very relevant to what we're going to be doing. And an important type of gate in quantum computing is controlled gates, which is in essence where you take it's a 2-qubit gate where you take a second qubit and you have it based on what its value is. It determines whether you apply a gate to the target. And keep in mind that since a qubit can be in a superposition of both 0 and 1, that means it can be both applying and not applying the gate to the target, sort of by some amount of magnitude, based on whatever the amplitudes of the 1 and 0 are. As said, this is essential for coupling the qubit states, and having that entanglement, which is part of the quantum magic that lets us do interesting stuff in quantum computing. And of course, there's measurement gates, which are the non-reversible ones and are how we get information out. Here's some quick little animations just to give you show you a quick demonstration of how particularly the H gate rotates a qubit into the Fourier basis. Sorry, I should really just say into a mixed state. And so now I can actually, with that said, we can talk about phase encoding, which is where I get to actually introduce the Fourier basis. So this is the computational basis, which is the classical one that you are used to seeing in computer science, where you just have switching between zeros and ones, and you can, for instance, do 2's complement to calculate this number here. The Fourier basis is a basis unique to qubits, where you rotate by phase in the superposition axis, and each subsequent qubit rotates by a factor of pi over 2. So this one's rotating by pi, this one by pi over 2, this one by pi over 4, this one by pi over 8, and so on and so forth. So that's the basis that we're going to try to encode. This is how we're going to start encoding numbers. So how do we take qubits from the computational Z basis to the Fourier basis? Well, the Fourier basis is particularly convenient for addition specifically, because altering the phase is very easy on quantum computers and is inherently a linear process. In essence, if I want to add 2 numbers, all I have to do is add the phase in that case. So how we apply the QFT, you start from your most significant qubit, that is the qubit that represents the largest factor in 2's complement, the largest factor of 2. You expand that qubit into a superposition state with a Hadamard gate. You rotate it with a phase gate, sometimes called a P gate or a C rotation gate. That's various names. The point is you rotate it according to the binary expression. Using a controlled gate, a controlled rotation gate, and you use the other qubits that are defining this number to apply that gate, and then you just go down this loop for each qubit, going down to the subsequent lowest qubits, and each one encodes a bit more of its rotation in. We'll see a picture of this. So for instance, this is for the approximate QFT, but also quickly here, right here, you can see the full QFT, where we start with a pi/2 rotation we start with the most significant qubit, and then the next most significant qubit applies its rotation gate, and then the next one, and then and then the next one, and each one is decreasing the size of the rotation by half. A nifty thing you can actually you start to realize is later rotations in this process approach the identity, because these rotations are getting tiny. The last one here is like pi/128. And because of that, you can drop them to a fair approximation and save a little bit of time and reduce your gate count, which is very important for maintaining coherence, especially with noisy intermediate term computers. So you cut those out, and this can, while an approximation on noisy machines, this can actually improve your accuracy because you lose less than you would have lost just by applying the gate, since the gate adds some noise. Okay, so that's the QFT, and now we want to approach the topic of addition. So as far as reversible computing, we first consider the reversible classical adder, where we consider adding two 3-bit positive integers encoded in 2's complement. We apply these gates, these carry gates, which are composite gates, and these are each composed of just control X. So this is a control not gate, and this is a Toffoli gate, or a controlled X gate, and each of these, this is how you make these composite gates. And the moral of the story is you can do this, and it requires 3n bits for it to add 2 n-bit numbers. Note also, I suppose I'll mention the black bar here tells you whether the direction of these gates are reversed, is all that which side that black bar is on tells you. Okay. So, that's the classical version. As a point of comparison, and part of why we're interested in the Fourier basis, is that in the Fourier basis, you can do a Fourier Add, which, as compared to the previous one, which requires 3n qubits, this requires 2 and just the qubits. You don't require any. You just need the qubits of the 2 numbers you're adding. Once the integer register to be updated to the sum is in the Fourier basis, that is to say, if this second register, this Q24 register, is the one that's going to ultimately house the sum of the 2 numbers, so for instance, in this first step, we're setting the state, the actual numbers. And the second step, we apply the QFT to the register that we intend to be updated into the sum, and then we apply these phase gates controlled by the first register, the register that's not going to be modified. It's just whatever number it's representing is going to be added to this second one that's currently in the Fourier basis. And it's not unlike the Fourier transform, a cascade of these phase rotations, and then we inverse the rotation and we measure it, and that's and function. Then once we get it out, this second register has the new sum on it. So the full quantum Fourier adder requires n² gates for n-bit numbers. And if we apply what I was showing you before, the approximate QFA, the approximate Quantum Fourier Transform, and in addition, you can apply the same truncation approach to this addition Fourier Add step, because you notice that you keep dividing by 2. You have pi over 2 and then pi over 4, and then you always step up once when going down in the Fourier Add. But the point is you always end up decreasing as you go down this line of the other register. You keep cutting your rotation in half, so you can truncate this just like you truncate your Quantum Fourier Transform. And that reduces you to the process to an n log 2n number of gates. Oh, and keep in mind, I'm just including barriers in this picture for the sake of clarity. You wouldn't actually want to include them because they would slow you down on the machine. Okay, so just to give a taste of what this looks like, here are some results on the of the approximate QFA on a simulator. So the top shows where I've only used the approximate Quantum Fourier Transform, and I'm not truncating the adder itself. Keep in mind, this is using 8 qubits, and at the top you can see what 2 numbers are being added, and these bins show you what any number that appeared as an answer that is not that was greater than 1% of the total probability. Otherwise, it would have been a very ugly picture. So as you can see, so that's the top, and on the bottom is where we do both the AQFT and the approximate QFA, where that is to say we do all the approximation steps that we've discussed so far. And a few things I wanted to note on this graph is this. I wanted to include this one, a 4 plus 96, to point out that something I've noticed with the Fourier adder is when you're not having to do very much. That is, my 4 is really just a 0, one single digit that is a 1, and the others are 0. You're particularly more likely to not have loss of fidelity by doing more and more approximation. Oh, sorry. The different bars show you the depth in the approximate Quantum Fourier, to the level of approximation. So if we go to depth 1, it means that we're cutting off. We only ever do one phase rotation gate. So I would exclude this one and exclude this one and that one, and so on and so forth. Obviously, in a tiny circuit like this, which is very much easier to see, you aren't decreasing the number of gates all too much. But it's worth. We'll see more on that in a second. Anyways, as I was saying, you can go to a deeper depth when you're adding numbers that are particularly small, and you probably won't lose too much. That is, or at least you won't. Though that's when you do the additional step of the approximating the addition step, it does seem to impact a very low depth much more. Now, one generally expects the optimal level to do the approximation is at log 2 of the number of qubits. So since we're doing n equals 8, that means that we expect depth 3 to be the most efficient choice. And as we can see, that remains pretty consistently true in either case. We're quite accurate. I gave you very particular examples. I generated them randomly. I've seen many more, and there are some odd cases on the simulator, but this is fairly consistent behavior. Okay. So
what is on the x-axis in these figures? These are the steps.
These are simply bins. So if I do 111 plus 50, I would hope that my quantum computer has the answer be 161, and indeed it usually does, though occasionally it screws up a bit flip or something, and it gives me a different number. And in fact, if you stop and look at where some of these numbers are, you can probably realize what bit is flipping that shouldn't have flipped. Certainly the difference between 100 and 116 is particularly telling, or at least easy to suspect. Anyways, so these are the final answers. They're out of order. Actually, I probably could put them in order, but I didn't see a need to. The point is, it's the solution you get out. Okay, so the Fourier Add results on an actual quantum computer. I tried a number of things, but I ended up the only one that really showed something meaningful, that without a whole lot of like error mitigation, and then just like squinting your eyes really hard, was on Athens. There are better quantum computers, of course. I just don't have access to them at the moment. If you've been keeping up with quantum computing, then you might know that the big news recently is Honeywell, which has come out with a machine possessing a quantum volume of 512, as opposed to the machine I'm running on here, which is a quantum volume of 32, which is still enough here. I would certainly love to work on Honeywell, but they've stopped returning my calls. Of course, that's a joke. They never started returning my calls. But in any case, on Athens here, we see that I've done some additions. First, I wanted to include just 0, 0 for a reason, actually, that I'll get to in a second. And we can see that as far as I did the same. I was hoping to do a similar test, because while hypothetically this is a simulator is perfect, and it's true that the simulators is agreeing that yes, the log 2 of n is indeed where you want to be for the AQFT. But I was sort of hoping to see if I'd find I was curious what I'd find here, which Athens is a 5-qubit machine, so this would be a 2. Actually, the target register is a 3-qubit register, and the ancillary register is a 2-qubit register. And I was curious to see if I could see any difference applied by the AQFT, but it was not particularly consistent. This is as far as what I got.
One question. So if I read this particular chart correctly, so does it says that you will be only correct? For example, you pick up any quadrant, you will be correct around 40% of the time in your answer.
Yep, that is correct. And as far as how you want to run on quantum computers, so far, one would not want to run on a quantum computer that wasn't running a circuit multiple times. But yes, you are entirely correct. If I were to just run this once, there's entirely a chance I would just get the wrong answer. It's just more often I get the right answer. And so, as I said, and I mean, to be clear, there are better quantum computers. Quantum volume is 32, though, is at least enough to see that I haven't gone to statistical noise. I tried to do, for instance, a Fourier Add on the Melbourne system, which has 15 qubits, but at a quantum volume of 8. But even trying to do smaller adds, I was and with as much and the AQFT, I was still ultimately decohering too far to where, as I said, if you squinted really hard, you could still start to see some patterns, but it involved a lot of business that isn't particularly profitable as far as what we're trying to look at here, what I'm trying to explain and get across. Okay, so multiply by partial sums is how we're going to approach quantum multiply, which is actually just a classical approach. You, in essence, break your integer x into a sum of one term for each binary bit in 2's complement, and you add that factor of y to the total. So x0 here is like the first binary bit, x1 is the second binary bit, and so on and so forth. And each time I add that factor of 2 to the total. The part of why we like this is because this is an approach to multiply that relies purely on addition. And it means that we can, it does, for reversible computing, it does require 4n bits for 2 n-bit numbers. But that is still linear as far as in n. If, as an example, the way we get to do this through just add is if we have x here as a 6 and a 5, or sorry, if we're multiplying 6 and 5, in essence, this is what this equation would be. Or you can think of it this way, where we start with the lowest qubit 0 on x, and that and we have 101, which is 5, and it gets zeroed out because of this 0, and the other two ones we shift over one space on our output register, and we just start changing setting the bits from there, and that's how we can functionally just go through our bits one by one and determine what we flip and what we don't flip. So we're going to use an identical strategy for doing our Fourier multiply. And to do that, the key is that we are going to do the same we're going to use the quantum Fourier addition, but we need to have them be controlled. Each step of addition be controlled by one of the registers, so that we can because that's how we are actually going to have these bits be controlled by whether this is, for instance, in this case it would be, in the quantum case, this 1 might be a superposition, so we would want to add a superposition of the whatever superposition the other register is in. So this process requires n cubed gates, and as I said, 4n qubits for 2 n-bit numbers. And if we apply the QFA, this is brought to n squared log 2n gates. So this is just a quick example of how, because so far we've always just been, all of my examples, the data I showed you was all doing classical additions. I just wanted to demonstrate real quick using the multiply, for instance, that you don't necessarily, you can, the quantumness of these processes, the reason these are very much quantum operations is because you retain the quantum character of your registers. So for instance, if I create these registers, this is just how you do it in Qiskit, and I set my registers, instead of just setting them to a number, I set them to a mixture of two numbers, and then go ahead and do my multiply. Here I have the pure output, and then here I just convert it to something more human readable. And you can see that you have this nice, as you would expect, near perfect split of shot. So these counts are, if I ran this circuit 10,000 times, and this is how many counts each time when I went and measured my qubits, or sorry, my register, my qubits, what the qubit state was. And as you can see, it was indeed in a superposition of these two different, each one was in a different state, a pair of two different states. So that's what we mean by quantum multiply and quantum addition, because we can also do them in superpositions. Okay, so now let's talk about quantum multiply on the simulator. As I said before, I wasn't able to, just as I wasn't able to push the quantum, really get a good look at the effects of the approximate QFT on a real machine, I wasn't able to look at it at quantum multiply. So all I have to show is a simulator for now. But here you have, for instance, 9 times 6, and we can see that and once again, the top is showing where I only apply the QFT, the AQFT, the approximation in the QFT steps, whereas on the bottom I do both the QFT and the addition steps, and these are, recall, these are inside this quantum multiply, because quantum multiply is just repeated addition. These are these two different steps of approximation I can do, and I wanted to take a look at, okay, from one to the next, what changes, what do we see? And first off, you do notice that the same depth seems to have maintained the same sort of optimal stage. This is a little bit different because before we were doing a n equals 8 case. Excuse me. So yeah, so the the depth is actually not quite, doesn't look quite as optimal as it did in addition, which perhaps is not too surprising. You expect the errors that which you were just verging on in addition to perhaps pile up a bit more when you're doing them repeatedly. So this might suggest that if you want to do an approximate quantum multiply, it may be better to go to a step higher than you did with than you would with the quantum adder. But I'm not entirely convinced of that. I want to see the scaling, more of the scaling before I can say anything with much confidence. Okay. Do note that just as we saw before, there's a big drop when you add in that extra approximation step with the quantum Fourier adder as well. Seen in when you hit depth 1, these consistently you seem to be able to still get a better approximation at depth 1 if you only do the approximate QFT. Okay. So as far as that's where we are so far. Where we're going is for quantum matrices. The thing to be aware of is they're very highly qubit intensive, as I said, I've started to get into a little bit into trying to do matrices, but most matrices are largely not feasible on real machines and not even feasible on simulators, because simulators, you're simulating it classically and you still have limitations on just how many qubits you can simulate. And in fact, the problem, of course, is that they scale much worse than the real machines. But if we, as presented here, a dimension d by d matrix would require d squared n qubits, which is part of why it's so qubit intensive. Fourier matrix add would require it would be a straightforward process just like you do classically, and so it would be a d squared n squared number of gates. And if I were to apply a naive Fourier matrix multiply, which is an n cubed classical algorithm, then unsurprisingly I get a similar scaling for the gates and the number of qubits. I apply classical algorithms, get classical limits. So keep in mind, of course, that this is my intention. This is my initial intention, but these have already been historically improved upon classically, and it may be possible that there's even faster algorithms that are specific to quantum computing. As far as just in the immediate future, I suspect my intention is to apply one of the classical ones that is about at n to the instead of n's cubed, it's like n to the 2.3 thereabouts, because that it looks like it should still be feasible, but we'll see. Other things I'm pushing towards is trying more of the doing matrix operations on the simulator, and hopefully eventually on real machines, and we are in the process of identifying some more of the details of these approximation steps that we've been doing. There's some weird behavior I've been noticing where mysteriously all even in my multiplies, suddenly I didn't show any of them because the picture is pretty boring. At all depths, it runs perfectly. You don't have any errors on the simulator. Which I'm pretty sure I've got a handle now on why that's happening, but I still need to look a little bit more into it. And as I sort of alluded to before, there's still some questions, particularly for the Fourier multiply, as far as what is the best depth to default to. And then explore quantum matrix properties, because as I said, I don't really know how to talk about quantum matrices is what I've come to realize. And I've been looking around and it doesn't seem like there's all that much work on explaining, on others knowing how to, explaining how to talk about them and what their properties are. So that seems like something we're really going to need to do, as I said, because these are precisely the data structures that quantum computers are going to best enable us to use. So that is largely what I had to present on. Thank you all for listening, and I would like to open the floor to any questions.
Yes, I have a question.
Sure.
What language did you write your example programs in?
Python, using the package Qiskit, which is IBM's language that they use for the IBM machines, although the Qiskit itself is designed to be applicable for other types of machines as well.
Okay, thank you.
Soham has a question, put in the chat box there. If you can see it, Bo, I can read it to you. Did you use any noise model in these simulations?
Not as of yet. That is a consideration. I've looked into noise models, but I did consider including them, but largely they would have, as far as for this presentation, they would have just abstracted what I was really trying to say and point out, and give really a lot of what I was showing here was really just trying to give you an example and help describe what process, how this encoding is working. So no, the short answer is no, but it is as far as looking deeper into the AQFT, until we can get better access to better machines. It is certainly true that the noise simulations are really are going to be a good way to try to actually get an idea of what it will be like on actual machines and answer some of the questions I described.
Great. Okay. Other questions?
A vote?
Yeah.
Yeah, I also have a comment about the optimal cutoff for approximate quantum add. So as I did in my quantum simulator, for example, adding two numbers below 20, I would only get 96% correctness by using the naive log of 2n. So I think the log 2n optimal cutoff is only when n is big enough. When the number of bits in the target register is small, you would not want to use log of 2n. So what I end up with is I applied a step function. So when n is big enough, for example, n is greater than 4, I use the log of 2n. But when n is small, I would just use the n itself. Yeah, so no, that's what I end up doing.
Yeah. No, I just didn't want to. I mean, I could have gone into that here, but I didn't want to steal your thunder, because that's pretty new stuff that you just only sent recently.
Oh,
so I didn't want to. I mean, not to. You are correct. You are correct. In fact, at this point, I think you have you have pointed out something that you understand better than I do at the moment. So, yes, I don't know exactly what the. It is true at low n, log 2n doesn't seem to be appropriate. What one should use, I don't know.
Yeah.
The one that you proposed in your email, though, without going into detail here, seems reasonable to me, but I suspect we'll need to look more into it more.
Okay.
Good, good. I'd like to just go back to the question I asked during your talk, Bo, for a moment. So this is the first time I actually see what you call quantum matrix. I find it to be a fascinating object. And I understood from your answer, it's not exactly what I had. If the words were used in my mind, I would have come up with a different situation, which is a coherent superposition of two matrices. And you have this answer that I like, that there's likely to be a relationship between these two. But if I could just elaborate for 1 minute, fraction of a minute, where I saw a possible connection to the physical application is when we do time-dependent basis function scattering problems. Until now, we have not used a superposition of initial states. We've just used a fixed initial eigenstate and do the time evolution with a well-defined time-dependent Hamiltonian, which actually depends on the initial state. If I were to, and I do want us to generalize this to the more realistic physical problem, which is a coherent superposition of initial states. But that means that the Hamiltonian is itself a coherent initial superposition of initial Hamiltonians, because you have a different Hamiltonian, if you like, for each impact parameter, and it itself depends on time differently as well. So not that we go into a big discussion now, but if you and Wen Yang and also Wei Ji is attending this seminar, could be giving some thought to that application side, that's where I feel a possible fruitful discussion could emerge. Not necessarily immediately, you've got your hands full, but certainly begin thinking about that as an application.
So in essence, you're talking about then you'd have like a quote unquote. I mean, the terms may change. This is completely just in this context. I use this term because I don't know what else to call it. Quantum vector. You would have one quantum vector for that initial state, as you put it, and then you'd have like a quantum matrix for the Hamiltonian. And then you sure, okay.
But we can work with small cases. Wei Ji has his, if you look at the paper that Wei Ji led as the application of quantum computing and talked about for us, it's a 7 or 8 state, 7 initial state problem, time evolved and quantum simulated and so forth. But that's with one specific initial state at a time. But the more general problem, which is the more correct physics, would be a coherent superposition of initial states. And each initial state has its own Hamiltonian, but coherently superimposed in this full scattering problem. Anyway, I haven't seen all the, it's not terribly clear in my mind, except that it looks like it's a possible connection with what you're working on. And just for everyone else's benefit, I would just comment that, you know, it was a shock to me to see how hard it is to do quantum addition, multiplication, and so forth on quantum computers. But that's because we are, you know, I am trained as a classical computer person, and I always think we're seeking higher precision. But I think the message you're conveying is many problems don't need higher precision. They need more generality, where probability distributions are the relevant vocabulary. And we have to think through the science application side to reconfigure the problem to be the more general problem, for which this could be highly applicable.
Mm-hmm.
So I don't know if I'm, yeah, go ahead.
And a big message sort of that I'm hoping to get across today is that is this idea of that eventually we're going to want to we really need to start to understand these like quantum data structures because they're not intuitive, but they're going to be one of the big things that quantum computers bring to the table because they're going to be very good at it.
Mhm.
And so knowing how they work, right now, most of the quantum computing that you see, we do it in the language of the computational basis and the versus the superposition basis. And you talk about, for instance, like getting the expansion of all of those basis states in that bit string. And what I'm hoping to kind of note on is, which is great, don't get me wrong, but just as it would be, you don't expect people to discuss, say, doing computational linear algebra in terms of bit strings. The expectation is eventually we really are going to need to develop how we are going to discuss quantum data structures if we're in as far as using quantum computers in the future.
Mhm, mhm.
Well, I have a couple of questions. So for your additions, I saw you were using two's complement. So are you doing that so that it can extend also to subtraction?
Oh yes, yes, which we can do. I didn't show it here because it's pretty straightforward from addition, but you're correct. Two's complement is part of why we can do it.
Okay, and then also that sort of could also extend to division. Have you looked at division as well?
Yes, the one problem that I started to realize is when broaching, so with division, you can do like modulo division, and that's pretty straightforward. That should be doable. The concern is as far as leaving just the realm of integers and going to, for instance, the realm of like fixed precision reals. I've realized that if I have a real number that needs to lose decimal places, I'm not sure I can do that, or at least I don't know how to do that on a quantum computer because I can't destroy information. So it's made me hesitate on how to go about going from integers to reals. So, and that is something that would be awfully useful when considering not just a modulo division, but like a division that would allow for fractions. So
All right.
we've considered. Yeah.
Go ahead.
We've considered division, but as of yet, I haven't implemented anything, and it's kind of raised some questions that I haven't worked through as far as how to go about it.
Okay, but if you do multiplication, it's repeated addition, division. One way of it could be repeated subtraction.
Yep.
Okay, and then the other question was about the probabilistic accuracy of the results.
Mm-hmm.
Have you observed if there is a relationship between the accuracy and how many iterations you go through?
Yes, especially on the quantum computers. If you do too many iterations, actually, if you do too few, then you don't get a good spread. It's not well converged. But actually, if you do too many, then the quality, like the quantum computer, like has different running conditions at any given time. And if you give it enough runs, then you actually have to start worrying about, well, maybe some of your later runs are going to start not be working as well because it's been running longer. the runs are generally very quick, but if you crank it up too higher, I have started to notice small differences in the degree of the spread.
Do you think it's possible to come up with like a formula which just shows the trade-off, accuracy versus the number of times you would have to do it? So accuracy versus time.
Sure, you might be able to. I suspect it'll be machine dependent. It will also probably be just like it'll be circumstantial, like time dependent in the sense of like one day it might run this way and another day it might run that way. So I'm not. So you could. I don't know how if I could extrapolate it though. I might be able to. You might be able to find some commonality between machines. But to be clear, I would only since I have only ran on superconducting qubit machines. I wouldn't expect the same behavior necessarily for. In fact, I know there's different behavior for instance, trapped ion qubits, as far as like how they respond to these like many shots and such things. Actually, I didn't quite show you, but I forgot to mention it. But on these runs, I wanted to point out that you notice here that the scaling is different on this one in particular, and this I included this one 0 + 0 in part because it highlights the fact that on a real quantum computer, especially superconducting qubits, you tend to have a bias towards the 0 state because that's the rest state. And so when it happened to be in the 0, 0, this is something I've started to see more consistently, slightly better results when it was whenever I was close to the whenever I was in the rest state of the machine.
So I do have a comment on Mary's comment. For the formula, you could try, instead of trying to do it too generally, just say I have consecutive runs. How many consecutive runs should I get to get certain kinds of accuracy?
Right.
Okay.
If you could come up with a, maybe a relationship like a formula, will be accuracy versus time trade-off.
Well, the other thing to be clear on is every circuit's going to also be a bit different. Like it's going to depend on my circuit depth. It's going to also depend on my the gate set that the system is using. But assuming it's if we can reduce our consideration just to like the IBM machines, which all use the same gates, for instance, it will depend on. For instance, that's why I couldn't do Fourier Multiply. No matter how many times I would be running, I would just get more noise from it when I was trying to run on Melbourne, because it was simply too deep a circuit for Melbourne to keep its qubits in a coherent state. So I'm not. Maybe I'm misunderstanding the comment, what you're getting at. But this would be then a thing that's also dependent on the circuit you're talking about as far as what accuracy you get.
Good. So maybe all of that could be formalized. That accuracy is a function of not just iteration, but also the circuit, the depth, the gates. I think if you just could come up with a formula and maybe I understand the differences. Maybe that we could make an abstraction and have a model, an abstract model, and then for the abstract model, say these are the trade-offs. And therefore, anyone who wants to design algorithms for such machines will have this as a guide.
Sure. I suspect the challenge will be as far as for a guide will be the question of, can we come up with something that holds a certain amount of consistency between machines, even if we restrict to just say superconducting qubits.
Right.
And certainly don't. It could go either way. I could imagine it turning out that it depends too much on the circuit, no, I'm not sure. It's that what you're proposing is a difficult problem. I can say that much, but I certainly don't mean to imply that it is a impossible one.
Okay, thank you.
Bo, I have a question.
Yeah.
Just following up. So if you run the same circuit on a real quantum computer with, for example, 512 shots, 1024 shots, or 2048 shots, would it give you a significant difference in the final probability?
In my experience, the difference between, for instance, 1,000 and 10,000 can make a difference just in the degree of. I mean, it all comes down to how much variation you're comfortable with. How well converged you want it to look, and then you have to. And then the other half of it is how noisy if we're talking about actual machines, how noisy the machine is, because the noisier the machine, the fewer shots you need to do before adding additional shots doesn't really make that much of a difference in my experience anyways.
So, okay. So I would imagine they'll be illustrating a trade-off between the qubit degradation and the number of iterations, right?
Mm-hmm. And of course, the circuit in question.
Well, very good discussion points, everybody. I think everybody has Bo's email address and can, if a question occurs to you later, email him the follow-up question. Thank you very much, Bo, for this very enlightening presentation. It really underscores in my mind, on the one hand, the opportunities that are out there, because everything seems to be in such a early stage of development. I think how each of the multidisciplinary participants can contribute is a challenge. I think we have some good questions from various participants indicating areas of expertise that could be brought to bear. So we should keep those in mind and try to spin off or amplify what you're doing with efforts that maybe take advantage of those areas of expertise. I promise to continue thinking about, and I started writing some notes here, the suggested application. It's not so direct as I initially thought when I heard you say some of the initial things you said. So I have to give it more thought. But there are others who are on this seminar who have also looked a lot at scattering problems and may have better insights than even I do. So, okay, let's thank you,
I
Bo.
have also just
Thank you very much, Bo.
Yeah, thank you very much.
Thank
And
you for the opportunity.
yeah, we look
Thank
forward
you.
to hearing more as time evolves here.